Hello, I welcome you all in this presentation related to the subject failure analysis and prevention. And we are talking about the failure analysis of the gears. In the previous presentation, I have talked about the failure of the gears due to the overloading and the fatigue conditions. Fatigue conditions are usually experienced by the gears during the normal operations. In this presentation, I shall try to talk about the failures of the gears and their identification of the causes. When the failures occur due to the deficiency in material or faulty manufacturing or there is a maintenance issue like that. So, as far as the content is concerned for this presentation, we will be talking about the three types of the case studies. You know that the failures of gear can occur due to the fracture or due to the wear and the plastic deformation also in case of the overloading and the low yield strength materials. Okay. So, here the case studies on the gear failures are due to the faulty say grinding where which is part of the manufacturing and like say to achieve the desired dimensional accuracy and tolerance, the grinding is done, and if the grinding is not proper, then it will leave behind the feed marks, deep craters and also the residual stresses. So, both will be encouraging the crack nucleation and then eventually fracture by fatigue. Okay. The maintenance is something like where if the maintenance is not proper means either the not proper lubricant has been used or the lubricant is not applied at all for a long time. So, or there is no systematic and periodic way of doing the maintenance. Okay. So, that can lead to the multiple kind of the wears in aggressive manner, which can be like adhesive wear, abrasive wear and leading to the significant change in the geometry of the gear tooth, and so eventually ability to transmit the power is reduced or the system starts improper functioning. Okay. Or the material which has been used for making the gear is not of the proper composition, is not of the proper structure also, or the manufacturing approach which has been applied is not compatible, is not good enough to impart the desired set of the properties to the surface and to the core. So, these conditions can also lead to the failure. So, how to establish if the failure has taken place due to these kind of the causes. Okay. So, we will be taking up three different case studies, then where we will try to see like if the fracture has taken place, then what would have been the reason behind the fracture. So, say this case study, the fracture caused by the faulty grinding. Okay. So, when the faulty grinding takes place, like the gear tooth surfaces when subjected to the grinding in appropriate manner, it can lead to the deep grinding marks. Okay. And it can also cause abnormally high temperature to the surfaces which are subjected to the grinding, and that in turn can lead to the development of the residual tensile stresses. Okay. So, both these factors are known to be a very good combination to contribute towards the crack nucleation and then fracture under the fatigue conditions. Okay. So, and especially if the grinding is not proper in the root section of the gear tooth. If the feed marks are there near the gear tooth where the stresses are high, or residual stresses of the high tensile residual stresses are being developed, then these will be simply adding to the externally applied stresses to nucleate the crack and cause their growth subsequently. Okay. So, this is what actually happens when the faulty grinding is done. So, a gear of the gear train failed prematurely after the 2 years of service. An investigation, when investigation was conducted, it was found like as expected the material of the gear is 0.25% carbon steel as per the design requirements. It was subjected to the case hardening to impart the desired higher surface hardness up to 1000 micrometer or 1 mm depth. So, this was also in light of the expected surface modification. Mechanical property studies carried out indicated the surface hardness of 45 HRC and the core of the like say 15 HRC, which means the properties imparted were also within the expected range. Microstructure study also indicated like for 0.25% carbon steel, when the surface is subjected to the case hardening by the carburizing followed by the hardening treatment. So, obviously it would be having perlite martensite or the martensite only at the surface and the perlite and ferrite in the core. Okay. Ferrite and perlite in the core, because it is just very hypoeutectoid steel of 0.25% carbon steel. Maintenance showed the normal lubrication. Okay. So, everything looks to be fine here so far as the investigation is concerned. Further investigation revealed that there was no misalignment, as it was observed from the temperature measurements uniform across the width, okay, and no skewed wear on the across the width of the gear tooth. So, that suggested like there is no misalignment. Visual inspection of the failed gear tooth indicated deep rough grinding marks, especially at the root of the gear tooth, and when the deep grinding marks are there, then they act as a crack, and if the crack tip radius is very low and the depth is great, then these will be increasing the stress concentration significantly, and thereby they will be nucleating the cracks very easily. They themselves are acting as a crack, and then the crack the crack and their growth will be further promoted with in presence of the deep grinding marks and the residual tensile stresses. Okay. Under the fatigue conditions, then these cracks will be growing gradually in a steady manner in the second stage and then sudden fracture in third stage. Okay. So, this is the nucleation stage, growth stage and sudden fracture stage. That is how the fatigue fracture will be occurring. But here the issue is the grinding, where in the deep grinding marks are nucleating the crack apart from the residual tensile stress. It was also observed faulty grinding led to the development of residual stress up to 250 MPa. Means if externally applied stress is 150 MPa, which is say well below the, say this is the design stress or well below the design stress, and then if there are already 250 tensile stress MPa residual tensile stress, then in nutshell in total the 400 MPa stresses will be acting, and these 400 MPa stresses may be much beyond the allowable stress level for the gear tooth, and that eventually will be causing the crack nucleation and then fracture. So, presence of residual stress due to the faulty grinding, presence of grinding marks due to the faulty grinding. Okay. Other conditions of the operations were normal, and the SAM study indicated the cleavage facets and the dimple at the core here. So, this indicates that the crack on its own led to the sudden fracture under the normal open operating conditions. So, in view of above, all these observations suggest that gear tooth failed due to the rough grinding, which led to the development of deep grinding marks and residual tensile stresses, and both these promoted the sudden fracture of the gear tooth. Now, we will take the another case study. So, here another case study is related with the failure of gear, where maintenance was not done properly. As I have said, the failure of the gear by wear can occur. Wear is a gradual loss of the material, okay, gradual loss of the material which can occur due to the adhesion when direct metal to metal contact comes in absence of the lubricant, or there is abrasion, means the lubricant is coming with the lot of hard abrasive particles in form of debris, and that will be promoting the abrasive wear, and the surface fatigue or the contact fatigue wear. So, surface fatigue wear due to the typical normal operation of the gears which are subjected to the fatigue under the high stresses, the cracks will be nucleating below the surface and they will be promoting the suppression or removal of the material from the surfaces of the gear tooth and change the geometry and morphology of the gear tooth surfaces. So, in this particular case study, what we will see that failure of the gear teeth, gear of the gear train failed prematurely after 5 years of service. When investigation was carried out, it was found that as expected material was fine, it was made of 0.25% carbon steel. It was case hardened up to the by carburizing up to the 1000 micrometer depth, and the properties were also as expected like 45 HRC surface hardness and the core hardness was 15 HRC. Microstructure also as per expectation martensite and the perlite mixture at the surface, okay, due to the carburizing and hardening martensite and perlite, and the core was comprised primarily the perlite and the ferrite. So, like say 45 HRC near the surface and 15 HRC in the core. Additionally, when it was checked, the gear tooth surfaces were completely dry and there was no lubricant. This is an important observation. Okay. So, we know that when the gear tooths during the operation come in contact with each other, in absence of any lubricant, what happens, the two comes very close, and what happens, like the two surfaces when they come very close to each other under the load which are being transmitted. So, under the pressure the two surfaces will be coming very close to each other. So, where what will be happening, the peaks and valleys present on the both the sides, they will be coming very close to each other, okay. They will be forming the cold bonds, okay, and due to the continuous relative motion between the gear tooth surfaces, the bond is broken and material from one side is removed. So, material from the weak side out of these two gear tooths will be removed. So, this is one possibility, like material can be removed from one side of these two gears which are messing. So, this is what will be happening when the lubricant between the gear tooth surfaces is absent in case of the poor maintenance. So, no lubrication leading to the situation of the direct metal to metal contact under pressure. Okay. So, and when there is a continuous relative movement between the gear tooth surfaces, this will be promoting the adhesive wear. Okay. And if the continuous direct metal to metal contact continues for longer time, then this will also be promoting the crack nucleation below the surfaces and eventually their growth at the surface, like say this is the surface of the gear tooth, the cracks will be nucleating and then eventually they will be reaching at the surface to cause the removal or delamination of a small piece of the metal. This is called surface fatigue wear, and these things will be predominating especially when there is no lubricant between the interacting surfaces of the gear tooth. So, absence of the lubrication will be promoting heavily the adhesive wear and surface fatigue wear. If the lubricant is coming with the impurities in form of the particles, debris, then they will be promoting the abrasive wear also. So, abrasive wear will be happening when the hard particles are coming with the lubricant at the interface between the two matting gear surfaces, that will be promoting the abrasive wear, and complete failure of the lubricant will be causing the adhesive wear and also the surface fatigue wear. Okay, so this is the background of this one, how the failure of the maintenance and proper lubrication can promote the wear. Assembly observation indicated the possibility of the misalignment due to and that was observed like more wear on one side than the another side, like this is the width of the gear tooth. So, say more wear is occurring in one side and this side is still clean, which means the contact the power is being transmitted, load is being transmitted from the only one part of the gear tooth surface, not the entire part, and that is why the gear tooth is subjected to the localized load transfer and the increased loading, and so increased wear tendency. So, visual observations suggested more wear on one side than other. Additionally, at the bottom, what was observed, like the fine debris, black debris powdery particle. So, here at the root of the gear tooth, the fine black powdery particles were observed. Basically, these powdery particles are like wear debris, and if we check or if we try to characterize this wear debris, then it usually comes out to be the oxides of the elements which are there in the respective gear tooth materials. Okay. And the this also indicated the fine abrasive, fine black particles at the root and deep craters on the tooth surfaces. So, the deep craters on the tooth surface primarily caused by the removal of the metallic pieces under the surface fatigue conditions. Okay. And NDT showed no major discontinuity and defect in the gear tooth surfaces, and the investigation about the operation condition indicated the normal operational loading. Okay. And the SEM indicated the oxidized surface with the abrasive marks, which suggested the gradual wear due to the adhesion, contact fatigue and abrasion. Okay. So, if we see here, what are the causes? Misalignment, no lubrication. These promoted the localized wear of the gear tooths, one, and direct metal to metal contact due to the absence of lubrication resulted the oxidized surface and the black fine powdery particles, that is the wear debris, and the deep craters indicated the occurrence of the contact fatigue conditions. Okay. And all these were promoted primarily due to the poor maintenance and the assembly conditions. So, all above suggested the failure of gear by wear due to the improper maintenance and also assembly that led to the localized wear at one end. Okay, so this is the next case study where the failure of the gear occurred due to the wear, and that wear was primarily encouraged due to the faulty manufacturing and the material that was used. Okay, so the failure of gears due to the loss of geometry. Okay, so this loss of geometry primarily occurs due to the wear, or it can also occur due to the deformation if the abnormal loading in the low yield strength materials if it occurs. A gear of the gear train failed prematurely after 5 years of service, and investigation undertaken showed that the gear was made of 0.15 carbon steel instead of 0.25 carbon steel. This was less than the specified, means there was a composition issue. Okay. Then the case hardened when the study of the gear tooth surface was carried out, it was the case hardening was done only up to 0.5 mm depth instead of 1000 micrometer or 1 mm depth. This is less than specified. So, the case hardening was improper. When the surface hardness was checked, it was found like instead of 45 HRC, now it showed only 35 HRC. And the core hardness was also 10 HRC due to the low carbon content. Microstructure also indicated in the same way, like it was more perlitic and less martensitic, and at the surface, and in the core it was more ferritic and less perlitic in the core. Okay. And maintenance indicated the normal loading. So, here if we see, there are three kind of deficiencies which are very much in line. One is the material issue, low carbon steel in terms of the carbon content. Carburizing is the another issue, it was not depth, so carburizing depth was not proper. Third, because of these deficiencies, the surface hardness was also not proper, like it was surface hardness was less, means the carburizing was not proper actually. So, the hardness was also an issue. And this was further confirmed by the predominating perlitic structure rather than more predominating martensitic structure. So, it was a perlitic martensitic structure rather than martensitic perlitic structure, and more ferritic and perlitic in case of the due to the low carbon steel. So, all these findings were in line actually. Okay. Why? Because we know that the composition, microstructure directly affects the hardness. So, increasing carbon content in the steel simply increases the proportion of ferrite. Okay. So, here increasing carbon content, say this is 0%, this is 100%. So, when the carbon is 0, you have 100% ferrite, and increasing carbon content, what it will be doing, it will be increasing the perlite percentage. So, here for 0.8% carbon we have 100% perlite, and in between like say 0.2, 0.4, 0.6 like that, if we see increasing carbon content will be decreasing the ferrite content, okay, and increasing the perlite content. Okay. So, these are the areas corresponding to the perlite, and this is corresponding to the ferrite. We know that the perlite is harder and stronger than the ferrite, and that is why increasing proportion of the perlite will be increasing the hardness, increasing the resistance to wear. This is just one aspect. When you have high carbon content, then the high carbon content, then what happens, due to the high carbon content, high proportion of the perlite, we get the higher hardness and higher strength. At the same time, the martensite whatever is being produced also shows the hardness variation as a function of the carbon content. So, hardness of the martensite also increases with the increase of the carbon content. So, when carbon content is say like say 0.5, then the hardness is here. If the carbon content is less, then the hardness is here. The point is, carbon content directly affects the hardness of the martensite and also the proportion of the ferrite and the perlite. Okay. So, therefore, it can be said that if there is any error or any issue related with the material composition, then eventually it will be leading to the inappropriate microstructure and inappropriate mechanical properties. Okay. So, the further investigation what it revealed, like there was no misalignment as far as the assembly is concerned. Visual examination showed the loss of geometry and shape, particularly due to the gradual wear, and equal wear along the width of the gear tooth means the system is properly aligned and it is a normal wear. Okay. No major defect was observed, normal operating conditions as far as the loading is concerned were observed, and same study indicated the abrasive marks suggested the gradual wear due to the adhesive contact fatigue and abrasion. Why? Because our composition carbon content was not proper, case hardening depth was less, and the microstructure were also not as per the requirement. So, all these things promoted the wear of the gear tooth surface even under the normal operating conditions, and that encouraged the material loss and so the modification in the geometry of the gear tooth surface. All above suggested the wear of the gear, failure of the gear by wear due to the improper material, that means the carbon percentage was not proper, improper manufacturing means the case hardening was not up to the desired depth with the desired set of the hardness values, and these in turn led to the lower hardness. And we know that the hardness directly affects the wear, especially under the adhesive and abrasive wear conditions. Okay. So, if we see for adhesive and abrasive wear, wear is inversely proportional to the hardness, means higher the hardness, greater will be lesser will be the adhesive wear, lesser will be the abrasive wear. But if it is so this logic is not equally applicable when we have the impact conditions like in erosive wear conditions. So, for adhesive and abrasive wear this is perfectly fine. Okay. So, now here I will summarize this presentation. In this presentation basically I have talked about the three types of case studies where the failure of the gear tooth surfaces occur due to the variety of reasons. Like in the first case the failure occurred due to the grinding marks. So, the grinding marks were developed due to the inappropriate grinding which resulted in the deep grinding marks on the at the root of the gear tooth. At the same time it also developed the residual tensile stresses, and both these factors like deep feed marks or grinding marks coupled with the residual tensile stresses, these nucleated the crack easily, and which eventually resulted the fracture. Then the second case study was related with the faulty maintenance, wherein it was found that there was no lubricant that resulted in the direct metal to metal contact and contact fatigue. So, metal to metal contact resulted in the adhesive wear and contact or surface fatigue wear. Okay. And that in turn in the long run led to the loss of geometry and the shape of the gear tooth. Third case study was related with the deficiency in manufacturing and material. What failure analysis suggested that the material of the gear was not proper, like it was of low carbon content. Then the case hardening was not done properly because it showed the lesser depth of the case hardening and lesser hardness of the surface as well. At the same time, and this happened primarily due to the varying proportion of the microstructure in the core as well as in the surface. So, it is very important that gears are not just designed properly, but they are manufactured, processed correctly to achieve the desired set of the properties. They are assembled appropriately and they are maintained properly for the longer life. Thank you for your attention.